Measuring star diameters. In the picture here, we see an illustration of the stars going from our low mass M star up to our high mass O star, and clearly shown that the M star has a small diameter and the O star has a large diameter. So here we see another connection with temperature and mass. High mass is going to have a large diameter, it's going to be hot. Low mass is going to have a small diameter and be cool. So they're all connected. But how do we know that an O star is this big? Where do we get that information? Well, there's two ways of doing this. The first technique is called lunar occultation. And of course, our moon is a ball. You can almost see the outline of the dark side there. And our moon orbits around the Earth, so it's in motion. Which means that in this particular picture, we could watch the moon eventually cover that star. And we can time how long it takes for the light of the star to disappear. Because it's not going to blink out instantly. It will take a fraction of a second, but it is measurable. And so using our knowledge of how fast the moon is moving, we can get an angular diameter of the star. So that tells us how big of an angle it covers in the sky, but it doesn't tell us that number in kilometers. We would need to know the distance to get the true size. And this technique is very limited because our moon doesn't cover most stars, so you're limited to the stars that are somewhere within the path of the moon, and they do need to be fairly bright because faint stars we would not be able to see. So this technique, although it works, is very, very limited. Binary systems gives us a different technique. So now we're limited to stars in binaries, but more than half of all stars are in binary or multiple star systems. So this we've got a much larger database that we can make use of. And so the idea is that as stars orbit each other, when they're side by side like this, we're going to get the most light because we're getting the light from both. But as one star moves in front of the other, it's going to block light from the brighter star. So it gets fainter. Then we're back to maximum again. And then we're going to block light of the fainter star. And so it gets fainter, but not as faint. Because we're not blocking out something that is as bright. Here we're blocking out a good chunk of a really bright star, so the total light is going to drop more. So we get this dip that goes much further down. When we block the light of the fainter star, we get a smaller dip in the light. And so this graph is called a light curve. We're getting how much light do we see versus time. The person who figured out how to use light curves to get diameters is this guy, John Goodricke. He lived in the late 1700s. And he's interesting because he was deaf and yet was a professional astronomer. He lived a short life, but he made this contribution using this idea that if you could time how long it takes for the light of a binary system to dim as each star passes in front of the other, we can determine the size of the two stars. So in general, we have points in our orbit. So if we're looking at two stars, when the smaller star first touches the big star, that is called first contact. And then when it has moved enough that that little star is now completely, well, let me hang on a sec. That little star is just inside the edge of that big star. That point is called second contact. So it has traveled a distance equal to, can't spell, hang on, a distance equal to its size. So it's traveled a distance that's equal to the small star's diameter. So if we measure this time, that's going to tell us how big that small star is. Similarly, for our big star, we can go from first contact to the position called third contact. So now the distance our little star has traveled is equal to the diameter of the big star. So again, we look at the time to get the size of the big star. We can also use this diagram to get the period of the orbit, because like we saw with the velocity curve, the time for the pattern to repeat is going to be the period of orbit. So our velocity curve, we were able to get the period of the orbit and the mass of the two stars. Light curve, we're able to get the period of orbit and the diameter of the two stars. So binary systems are very important when it comes to trying to measure a star.